No, this is actually my first time teaching Geology 105. Yeah. So before that, I was the TA for the lab. So that was my first time doing a lecture. This spring, I'm doing 203, which is Earth surface processes, which is like a precursor to geomorphology. So it's what I study, which is fun stuff. It's more the nitty gritty of like how Earth changes over time. Thank you. I'm gonna need it. All righty, guys. So, last day for new stuff. Today we're gonna be talking about super fun stuff, meteorite impacts and extinction events, all the doom and gloom stuff about geology. So we'll be talking about that. As per usual, keep an eye on Canvas stuff. If you haven't gotten stuff in, get it in soon. Final grades are due February 9th, which is a week from today. So if I don't have it and it's not added to your final grade, then that's it. Can't change it once it's submitted. So keep an eye on Canvas. All those points do stack up. So more stuff you do, the better you do on your reading assessments, your quizzes. That's really going to help your grade. So your exam grade is not the end all be all. Yeah.
The climate change project this summer,
Uh-huh.
we're supposed to submit it today. If you will, but the assignment also
Ooh, that's fun. So you better get it in that 1 minute time span. I'm just, no, I'll fix that. So what I'll probably do is just change that to be due Friday at the end of the week. Just because you got other stuff to study for this week, I'm sure. So I'd rather not stress you guys out with getting that assignment in. So I'll change that on Canvas right after class, and then we should be good. Anybody have any other Canvas problems? I got a couple of emails this morning. I think I fixed them. Anybody on Zoom? Do you guys have any issues with the Canvas stuff? Judging by your silence, I'm going to take that as a no, and everything is hunky dory. So, all right. So let's talk about impacts. So, 2013 in Chelyabinsk, Russia, there was something known as an airburst. So this massive rock hurtling in from space entered the Earth's atmosphere and created what's known as an airburst, which we'll talk about in a bit. There are a number of casualties with this. Key thing to keep in mind with this is that it didn't fall to the ground. So you can see it from a dash cam footage. So for a quick second, people of Chelyabinsk thought they were being bombed. There was an attack imminent. Turns out it was just a rock from space. So you'll notice as it's getting closer and closer to the surface of the Earth, it's getting brighter and brighter. That means it's burning up all the friction from the airflow flowing over that rock as it's entering the atmosphere. It's going to start to build up heat. And as you build up heat, you're going to build up that volatility inside the rock until it explodes. So this is a relatively small asteroid. So this is moving at 7,000 meters per second. That's the equivalent of 15,600 miles per hour. Keep in mind the fastest airspeed record that we have in Earth's history, fastest that we can fly in an airplane on the Earth's surface, has been, I think, 7,000 miles per hour. So this is moving twice as fast as the XR-15. So not as fast as the Apollo astronauts going to the moon, but then again, they don't have air resistance to take into effect. So it didn't reach the Earth's surface, as I said, it exploded in the stratosphere. So the problem that caused all of this, the casualties, I don't think there were many deaths, but there was a lot of wounds from glass. So as it's approaching, it's getting brighter, So people see that because this happened at night. So they see the just outside getting much, much brighter. So maybe they think there's a fire, maybe they think there's a gas explosion or something going on. So they go to the window, that burst happens, they see it, they're still looking at it, and then that shockwave finally hits their window, sending glass right into their face. So that was the main casualty that happened in Chelyabinsk at this specific area. So this was a huge amount of energy released as a shock wave. Luckily, it wasn't at the surface. Otherwise, it would have been a lot worse. Probably would have damaged a lot of roads, a lot of buildings, a lot of structural damage. But this is the biggest one known to enter the atmosphere since 1908. So this is a pretty big one. And we'll talk about each of these as we go along. So that one in Tunguska in 1908, that one hit in Siberia, just a few thousand kilometers away. That wasn't a very populated area. It was noted by some hunters and fishermen in the area, but didn't really do any real damage to human populations, although it wiped out and flattened around 2,000 square kilometers of forests. So whenever stuff is entering the atmosphere, keep in mind we have multiple levels of our atmosphere. So we have the troposphere, where we exist and where all of our weather patterns and temperature patterns happen. So that's where we have our condensation, our precipitation, our water cycle all happens in the troposphere. Volcanic ash sometimes can get higher than the troposphere and enter into the stratosphere. Stratosphere is where our ozone is. Remember O3, ozone. Whenever ozone is in the stratosphere, it's really good for us. Whenever ozone is in the troposphere, it's really, really bad for us. Not a good gas to breathe in. But when it's in the stratosphere, it helps protect us from radiation, prevents us from dying from skin cancer at incredible rates. Then we get to the mesosphere, where we get a lot higher in our altitude. We're at around 50 to 85 kilometers above the surface of the Earth. And then the thermosphere, we're approaching space, and we're going out, further and further into orbit. So yeah, as I said before, we had a huge burst of shockwave coming out, 1,500 people injured, luckily no deaths. It was so bright that it was 20 times brighter than the sun. And we're going to be using this term a lot. I use this term as well, bolide. We use it in astronomy as well as geology. So in astronomy, and it's an object brighter than the moon. So in this case, it was a bolide in astronomical terms. It was super bright. It was brighter than the sun. It's got to be brighter than the moon. And bolide for geologists, we're talking about the actual rock itself. It's an object capable of impact. So it is some massive rock that has the capacity to hit Earth. Because we're geologists, we care about what happens on the surface of the Earth. So that's why our definitions are tied to that. So how did we miss something like this? Well, first of all, tracking rocks in space is really hard, and there's a lot of them, and they're really small and they're moving really fast. So it's really difficult, but we've gotten a lot better at it over time. So the problem is anything smaller than 20 meters, we didn't see it as a real threat. We thought, okay, it's going to burn up in the atmosphere just because of all that air resistance, all that friction built up. It's just going to disintegrate as it enters into the atmosphere. But this one was also only 20 meters, and even though it burnt up higher above the surface, still caused a lot of damage. So a lot of astrophysicists focus on larger objects, what they call planet killers. So if this hit the surface of the Earth, it wouldn't destroy the entire planet. Probably would have flattened everything around, caused a lot more damage, but it wouldn't have been completely catastrophic to all of human civilization. So we've only spotted around 500 asteroids of that size. So back in 2011, NASA announced that they found roughly 93% of what they think are what are known as near-Earth objects. So there's still an unaccounted for number that they think could still be orbiting. The reason they know that they have 93% of it is because they can sense these gravitational pulls, but they can't find it where it is specifically. So they know the gravity is there. If the gravity is there, then some mass has to be there, right? But they can't spot it themselves. So we still have a lot of work to do in tracking these things. So these things always come from our near solar system. So Earth is obviously formed from a bunch of these rocky materials impacting and colliding together 4.6 billion years ago. So all of this cosmic dust, all of these rocky portions kind of amalgamate, get stuck together. and they end up building up their own mass. So this one specifically came from the Oort cloud, which is that little belt right between Jupiter and where is that? Jupiter and Mars, I believe. Nope, no. Yeah. So Jupiter is a really important planet to have on the outer part of our solar system because it's such a huge planet. It's a gas giant. It has a huge gravitational pull. So anything that comes into our asteroid belt is going to enter that orbit, and for the most part, it's going to stay in that orbit. If we didn't have Jupiter pulling that stuff away from the center of the solar system, we would get impacts a lot more common. We would get a lot of flybys from asteroids coming in from the Oort cloud and flying into Earth or past Earth. Our chances of impact would be a lot higher if we didn't have Jupiter. So thanks, Jupiter, for being super huge. So we also have asteroids out here in the Oort cloud. This is mainly rock and metals, all those ores. Asteroids are really rich in rare earth metals that we can't find a lot of on Earth. And we'll get to that in a second as to why we can't find a lot of them on Earth. Also, we have this thing known as the Kuiper Belt, way outside. This is where we have comets. And the difference between an asteroid and a comet, comets have a lot more gas content, a lot more liquid inside them. Whenever comets fly past Earth, we haven't had experienced a comet hitting Earth in human timelines, but we see them whizzing past Earth. The reason we can see them so brightly is because as they get closer and closer to the sun's rays are going to vaporize all of those gases and fluids and water vapor that's trapped inside that rock. That's what gives it that brilliant spectral tail that you see whenever it flies across the night sky. Asteroids, just those pieces of rock, as they get closer to Earth's surface, they don't get brighter until they start to burn up as they enter the atmosphere. So whenever you see something called a meteor shower, that's stuff falling into the Earth's atmosphere and it's burning up. A comet, however, is whizzing past Earth. It's not entering our atmosphere at all. It's just the interaction with the sun's rays is going to create that spectral tail. Yeah, so rock, ice, all these gases are going to give it that tail that we see. So up top, we have Halley's Comet, which you've probably heard of. It's probably one of the most famous. These things, since they're entering an orbit around the sun, we can time when they show up, and we can see whenever they're going to whiz past Earth. So these things come close to Earth, for specifically Halley's Comet, every 75 to 76 years. So that we'll see our next one in 2061. So keep an eye out for 2061. That'll be a fun time to see Halley's Comet. The Swift-Tuttle Comet is every 133 years. It has a much more elliptical orbit, so it takes a little longer. Okay, so we have a bunch of different terms here. Meteoroid, meteor, meteorite. How do we differentiate between them? So first we have asteroids. Asteroids are all out in that asteroid belt, circling right in front of Jupiter. They're out in space. They're out in the astral plane. So they're asteroids. If an asteroid comes close to Earth and comes into Earth, then it's a meteoroid. So you can see our layers here. We have troposphere, stratosphere, mesosphere, thermosphere. Once we get into the thermosphere with an asteroid, it becomes known as a meteoroid. Then if it keeps coming in and starts to burn up in the atmosphere from all that friction, that's when it's a meteor. So think meteor shower. We only get meteor showers when they burn up as they enter the Earth's atmosphere. That's why it's called a meteor. So an airburst like the one that hit in Chelyabinsk. Goddamn Russians. So that one was a meteor. It didn't impact the actual surface of the Earth. It was an airburst. So that was just a meteor. And then a meteorite is once it makes impact with the surface. Anything that makes impact with the surface from space is going to be known as a meteorite. So keep those terms in mind. There may be an exam question on it. So we can see some of these on the surface. This rock is in Namibia. It's very large. You can see that person to scale to the right. So since this is on the surface of the Earth, which one is it? Is it an asteroid, a meteor, a meteorite, or a comet? A meteorite. Very good. I love when you guys pay attention. So this is the Hobart meteorite. It is around 60 tons. It is the largest single piece of iron that we can see on Earth's surface. So we have ore bodies of iron, but those are in like small veins that you have to dig around and find. We have huge ore deposits, but we don't have huge chunks of pure iron naturally occurring like this. This is purely from space. So that's pretty crazy that we have stuff like that. So meteorites are really useful for us because they can tell us a lot about the solar system. Because obviously anything that we have on the Earth's surface tells us a lot more about Earth than it does about the solar system. Maybe if we look into the deeper parts of the Earth, we can learn more about the formation of the whole solar system. But really in these rocks that we get, these fresh samples that we get, we're learning a lot more about the space around us. So this fossil meteorite is known as the Österplana. It was found in Sweden. There's just this limestone quarry that they were digging in, Ordovician limestone quarry. So if it's Ordovician, it's limestone. We're in this shallow sea environment when this thing fell. So it falls into this shallow sea or lagoon. It gets covered up by all of these lime minerals, all the calcite, all the calcareous organisms die, they solidify, and it locks that fossil meteorite inside that rock. So this one is really, really rare because it's told us it's so chemically different than any other rock we've seen on Earth. It's really rich in iridium, it's really rich in chromium, all these rare earth metals that we don't see a lot of on Earth, but they're really, really enriched in this specific rock. So we've learned a lot about these. So we get a couple of different types of meteorites. So we can have stony meteorites where there's more rock than metal. So all those greens, we have pyroxene and olivine. Remember, olivine and pyroxene are our mafic rocks that we get deep in the Earth's mantle. They don't survive very well at the Earth's crust, but whenever they come from space, they're a lot more resilient, as you can imagine. So they contain a lot of different types of metals. So some of these contain up to like 7% nickel. Remember, we don't have a lot of nickel on top of the Earth. Most of our nickel is in the center of the Earth. So keep that in mind. So whenever these chondrites fall, as all that friction creates and generates that brilliant white light and heat on the outside of the meteorite, that's going to induce a chemical change to the exterior of the rock itself. So if you look at this one on the right, you can see it has like this greenish, darkish tint to it. Looks very different than the green on the interior, right? That's from all of that friction heating the exterior of that, honestly creating this type of crust, basically, on the exterior. So not only does that help it survive just entering the atmosphere by creating that more resilient crust, it's also going to help it survive the weathering on Earth. We talked about olivine being from the mantle. We don't see mantle rocks that often on the Earth's surface, right? They weathered and break down preferentially. So whenever it has that crust over top of it, it's going to protect it so we can actually see these minerals up close, and it stops them from just weathering away and breaking down. We can also have ones that are heavy in metals. So we can get some iron nickel meteorites. They develop all these weird geometric patterns in these latticed layers. So these are known as Widmanstätten patterns, founded by a German geologist. So all of these iron and nickel alloys just weave together in these rocks. And whenever you cut through them with a rock saw, you get to see all these really cool patterns. So usually these are formed from really slow cooling rather than rapid cooling. So these are, because they're so rich in iron and nickel, they're a lot denser than the same type of iron and nickel deposits you would find on Earth. They're like 3.5 times denser, just because they've amalgamated in space, so they've preferentially weeded out all the other like noise, basically. So they're a lot heavier than stony meteorites, and they're much heavier than any rocks that we find on Earth's surface. So some of you may have been lucky enough to be here. This is Barringer Crater in Arizona. This is the first like true impact crater that we've discovered on Earth. As America was expanding west, they came upon this crater and they were like, whoa, what happened here? So this really drove the study of astrogeology and planetary geology, and how we look at Earth's history from stuff in space, and how Earth is basically in the middle of this whole cosmic shooting gallery. So this one was from a meteorite a little larger than the one that burst in Chelyabinsk. It's 30 to 50 meters versus 20 meters. So you can see, it's hard to see in this picture, but there's a road leading up to the crater, and those are buildings. So this thing is really big for something that was only twice the size of that Chelyabinsk airburst. So this happened 49,000 years ago. So in terms of geologic history, this is relatively recent. And it created this huge impact crater. You can see that the rims of this crater are raised, and there's a bunch of what looks like broken rocks around that rim, which is known as the ejecta blanket. And we'll talk a little bit more about the structure of an impact crater in a bit and how to recognize stuff. So the key thing to keep in mind is, if you look at the center of that, there's really nothing in there. Nothing's left. With every action, there's an equal and opposite reaction, as we know. So if you were sending some type of rock into the Earth at such incredible speed with such incredible force, it's going to disintegrate that rock on impact. So you're not going to have a lot of stuff left over. So if we're comparing sizes, that's a 747. That's a Coast Guard class cruiser. The Chelyabinsk meteor is in the middle of there. The Barringer crater is a lot bigger. The Hoba meteor, that one that created that huge piece of iron that's left over, that was only 9 feet. So it had so little mass that it was able to survive, and that's why we have such a large chunk of it. And then the Tunguska comet, which we have at the bottom here, 330 feet, 100 meters in diameter, absolutely huge. So we've seen craters in this class before. So we have our calderas, our volcanic craters. So, and they have their own unique features, right? But let's see how they're different from meteorite craters. So our origin here is the eruption is pushed out from underneath the surface. So that huge magma chamber beneath it is pushing all of this stuff up to the crust, and we're developing and we're building pressure with our high silicon, high felsic magma on top, a lot of viscosity, building up that pressure with all the volatiles behind it. All of them happen at similar locations based on tectonics. So these only happen at sometimes hot spots if it's underneath a continent or a continental crust. But most of the time we're dealing with subduction zones where we're melting some plate underneath some continental crust, and that's where we're getting our viscous magma, our volatiles, the stuff that we need to build up enough of a magma chamber to have such a violent explosion. Temperature and pressures regarding the two of them is much lower for volcanic rock. Whenever we have meteorite impacts, that pressure is instantaneous and it's very, very high. And obviously, where the temperature and pressure is coming from is going to be different. Obviously, one is coming from space, so up. The other one is coming from the center of the Earth, so beneath. So that's why we're able to tell the difference between these two whenever we see each of these on the Earth's surface. So we can have different types of impact craters as well. So real simple ones. So Barringer crater that we just saw is a really good example. We have smaller objects. We just have that perfect bowl shape, the raised rim, and all the stuff that was in that bowl, it has been ejected out to the sides of the rim. So really simple shape, not a lot to write home about. It's really simple to understand. Other ones that we have can be very complex. So whenever we have a really, really big impact, we're going to influence a wider range of the local geology. So if we influence that wider range of geology, we're going to change the way the Earth is going to shape around that crater. So this is Mestadston Lake in Canada. It's near Ontario. So around 36 million years ago, we had this big impact in this area. Where are our temperatures? Where are our temperatures? Okay, we generated temperatures exceeding 2,370 degrees Celsius. So incredibly, incredibly hot. And this actually induced global climate change from this impact. So we can see in our proxy records and our ice sheet records, a change in our global temperature just from this impact whenever we cross-reference them. So if we take a profile, we cut that simple crater in half, this is what we're going to end up looking like. So we have the natural bedrock formations on the side. As you can see, all that force from the impact has uplifted the sides of this crater. So that's why we have that raised rim. So we have this big bowl-shaped depression. We have these deformed rocks from the initial crater. And then because of all of the heat that we get from these impacts, because of all the pressure, we're going to metamorphose some stuff as well. So all of these lenses of what's known as breccia. Breccia is similar to other sedimentary rocks where you just mash stuff together. Breccia just indicates that all of the pieces are really angular. So because they're angular, we can say that, oh, a really violent event created this and nothing has like rounded those edges out before it conglomerated into a rock. So we have fractured bedrock around it, indicating there is a huge impact. We get the present crater that we see with all of these melt fragments coming in. Sometimes we can get, depending on the environment, we're going to get some deposition of new stuff in that depression. It's just a hole in the ground. It's going to fill up with water at some point, and water is going to bring all sorts of other stuff into it. But in the case of the crater in Arizona, really dry, not a lot of rain, you're not going to get a lot of sediment going into it. So all of those sediments that get into it are actually windblown, and you can map that out as you look at that profile for that one specifically. Or we could have a complex crater. This is what we're looking at here. So we have the central peak of this impact crater in the center. Whenever you think of a drop of water into a glass of water, there's that one like peak that happens right as it drops in, right? That rebounding effect. You're gonna have the same thing with the rock surface of the Earth. So that central peak is basically that rebound effects that you get from the initial huge impact. It comes back up and it kind of solidifies based on the shock. So you have that central peak, then you have the inner basin of the peak ring where the actual impact happened. Then all of that raised rock around is going to destabilize all of these crustal blocks. You're going to get all these faults that form. And whenever we have faults, with a depression and void space in the center, we're going to get normal faulting. So all of those faults are going to fall towards the center, and that's going to increase the width and diameter of the impact basin. So we're going to fill up with all this impact breccia, all this stuff that finally settles out. And then after it's all filled in, we're going to continue our regular geologic processes. We're going to fill in stuff with sediments. But because of all of the underlying faults, we're going to develop new faults on the surface of that new stuff on the surface. So we continue to see similar faults because it's still kind of subsiding, still relaxing from that initial like shock that it received. So these impacts are really rare, but they definitely happen, and we can see them all over the place. The problem is, even if an impact happens, geologic forces are going to act upon it. So it is possible that we can get an impact and then just so much erosion and weathering has happened that it's just wiped the record of it away. So we can only map out and predict, map out and understand where impacts have happened if we have the record of it. Otherwise, we have no way of knowing if it happened or not. So this is just in North America, and we have a bunch that have impacted the Earth's surface right here in North America. All those dots are an impact crater. They're pretty large too, in certain cases. But as you can imagine, like the stuff, once we get up north, we have a higher density of impact craters down here, much lower density of impact craters up north. Part of that could also be due to just being covered by ice. Can't really see it if we can't see the surface of the actual Earth. Also, we have two big oceans on either side of this continent. So if something falls in the ocean, we're probably not going to see it for a very long time. And keep in mind, ocean is where all sediment eventually goes. So if there is an impact crater, it's going to get filled in with sediment relatively quickly. So it's really hard to find impact craters on the bottom of the ocean. So we can see so much more impact craters on the moon than compared to Earth. Why is that? What does Earth have that the moon does not? Everything, yeah. So we have an atmosphere. Atmosphere burn is like your first defense against asteroids. Anything small that would usually hit the Earth's surface is going to burn up in the atmosphere. When we have erosive forces on the Earth, that's going to wipe away any record of anything that is impacted. Moon doesn't have that, of course. And most of, as we mentioned, most of those impact craters are probably going to be underwater just because 70% of the Earth's surface is water. So we've got a large amount of the Earth's landmass that we can't see. So we know the Earth is 4.6 billion years old, but real early in that formation of the Earth, we had a real big event. So at this time, 4.6 billion years ago, there were 21 planets orbiting the sun. Most of them ended up colliding with each other, and Earth was just lucky enough to be collided with Theia, which is a protoplanet around the size of Mars. So this collision happens, their orbits intersected, so you have this massive collision of these two planets. As you get this collision, you're going to mix all of these rocks. You're going to send rocks out into space. Some of those rocks end up conglomerating in an orbit around the Earth, and that's where we get our moon from. This specific impact gives birth to our moon. And as we're breaking down all these rocks, we're combining the two planets, and they're going to find a center of mass. center of gravity. They're going to conglomerate into what we know as Earth today. So the reason we know that the moon comes from the Earth is because if we sample rocks from the moon, sample rocks from the Earth, the moon's rocks have the highest amount of silicon, highest amount of some nickel, aluminum, same stuff that we have the most abundance of on Earth. So other rocks that we've seen from space don't have silicon, don't have aluminum. So it makes sense that the moon had to come from the Earth just because we're so similar in our geochemistry. So here's another impact crater that we had 2 billion years ago. This is in South Africa, right just north of Lesotho. It's the largest impact crater that we can see on the surface. So this meteor was 5 to 10 kilometers across. Think about how large that is. 50 meters is half a football field. 500 meters is 5 football fields. So that's 5,000 to 10,000 meters. That's a huge, huge meteorite. So whenever the crater first formed, it was around 300 kilometers. And you can still see that remaining ring, even though a lot of that has filled in. Because this is Earth's biggest and largest impact crater, UNESCO doesn't just protect like human history sites, they also protect natural history sites. So this is on that World Heritage Site list. So it's naturally protected. You're only able to mine in certain areas. And we'll talk about mining when it comes to craters in a little bit. Or actually, we'll talk about it right now, actually. So this is the Sudbury crater. This is in Ontario, Canada. It's the second largest, number 2. This one was only 10 to 15 kilometers in diameter. Still pretty huge. So the rock fragments from this you can find all over the Earth, just because of how huge the impact was. You can find a couple of them in Minnesota and trace them back to here in Sudbury Basin. As you can see from the imagery, it's really hard to see on the ground. But once you start mapping things out, you're going to find a similar shape to stuff. So something that geologists are really good at is drilling holes, mapping stuff out from the bottom up, and then correlating that over a geographical area. Once you have all of that data, you're able to combine all of this into a geologic map and then a profile. And that's what's gonna really define how we found this impact crater. The shape of these deposits could only happen in an impact crater. It couldn't be a volcanic crater because we don't have any volcanism in this area. But because it's a basin, because of its depression shape, because of the deposits we have here, that's gonna be how we determine it's an impact crater. So Sudbury Basin has some of the biggest and largest deposits of nickel and copper in the world. Nickel and copper, really common in asteroids. So that's going to be another indicator that this was an impact crater. Another thing that we have a lot of in Sudbury Basin is platinum. One of the biggest deposits of platinum in the world. Platinum is very common in asteroids. Platinum is also a very useful metal. Everything from your catalytic converter has a lot of platinum, and platinum is at an all-time high at the moment, which is why there's a bunch of catalytic converter thieves out there just chopping your your catalytic converter off of your car. And it's because it has a lot of platinum in it. The platinum helps to take a lot of the emissions out of your exhaust, so all you're left with is CO2 and water vapor rather than like sulfuric acid and all this other stuff. But because of this impact crater, it basically enriched this area with all of these precious metals, opening up a huge mining industry, all from space, basically. Only place really outside of Norilsk, Russia, that you can find platinum and other metals like that. All right, 65 million years ago. We've got the one that you're probably most familiar with. This is the Chicxulub crater. It's off the coast of the Yucatan Peninsula. The third largest bronze medal. So because it was just off the coast, as you can imagine, displacement of water is going to cause a tsunami. So this one caused a devastating tsunami. And because it's creating a depression, after it has that initial shock wave sending the tsunami water out, you're creating now a void space for water to slosh back in. So you get the sloshing back in, you're displacing water again, it's going to slosh back out. So you're just creating tsunami after tsunami just from this sloshing effect and creating this depression right in the ocean. This is the one that wiped out the dinosaurs, which is why it's so well known. And we're going to talk a little bit about why it wiped out the dinosaurs. Now we get to the Papagai crater, 35.7 million years ago, fourth largest, 100 kilometers in diameter, but the meteorite itself was only 5 to 8. So this one's really interesting because all of the shock and pressure created impact diamonds. As we know from what diamonds are, diamonds and black carbon have the same exact chemical makeup, same exact thing. They're both made of carbon. But a diamond, if you take carbon and you put a lot of pressure on it for a long period of time, it's going to solidify and form into a diamond. If you do the same thing rapidly, you get a less impure diamond, but it is still incredibly, incredibly hard. So this is mainly used for industrial uses. So you'll have diamond-tipped drill bits or saw blades. They can cut through most hard rocks, hard materials. So these are really, really important for industrial use, not really for getting an engagement ring for your significant other because they don't look as pretty, but they're still very, very useful to industry. So we also have our own impact crater not too far from home. This is the Chesapeake Bay crater. It is the reason we have a bay in the Chesapeake. That's the largest one in the US, 85 kilometers in diameter. So this one was discovered by David Powers, no relation, sadly. He described within minutes, millions of tons of water, sediment, and shattered rock were cast high into the atmosphere for hundreds of miles along the East Coast. So this thing created something as deep as the Grand Canyon, instantaneously on the East Coast. Imagine you're driving to Philly and boom, there's a Grand Canyon there in an instant. That's crazy to think about. So because of where this is located, it's one of the best preserved ones as well. Even though we can't really see it on the surface, all of that sediment, because we're even 35.5 million years ago, the continental shelf is a lot further out, and there's a lot of erosive capability coming off of the Appalachians. We're still developing a lot of sediment deposits in there. So that rapid burial of all that sediment on top of the crater helps preserve it really well. So that's why we can see it so well with geophysics and drilling. So it's been really beneficial to learn a lot about it. So this really impacted, as you can imagine, Virginia, the Delmarva Peninsula, and that's really why we have all of this weird space in what you see here. If we had a more natural system with no impact craters, we would have a bay that looked a lot more like Delaware Bay, where we have a narrow mouth at the river and it widens a little bit, and then there's sedimentation on the other sides. But we have just all this irregularity inside Chesapeake Bay for some reason, and that's mainly because of the impact crater itself. It's creating these slumpings, all these normal faults that slump and subside. So we'll see a lot of that along the sides of the Chesapeake. So this is what that initial impact crater looked like if we put it on today's map. So right at the tip of the Delmarva Peninsula, we have the inner rim. The outer rim expands into the greater Chesapeake. I'm going to need to do a little bit more reading about line of equal dissolved solids concentration. Yeah, I'll have to get back to you on what these ISO lines are, these pink lines, because they're connecting equal lines of something that has to do with dissolved solids. I'll have to read the paper again and get back to you on that, on what that is. But you can see that the deepest part of the bay is right where the impact crater ended up being. So that really, really makes sense. As you can imagine, the structure of this impact crater affects groundwater because it's impacted where sediments are, where faults are. Remember, groundwater is going to follow the path of least resistance. So if it has a fracture, it's going to preferentially flow along that. So this could potentially become a problem if we have rising sea levels. All of that saline water is going to infiltrate into those fault systems, enter the groundwater systems of most of the farms on the coast. If you drive down south for quite a few miles, you'll see nothing but farms, and they have those irrigation pumps where it's the pump on the sprinkler system that circles around in these large circles, sprinkles water on their crops. They're pumping all of that directly from the groundwater. So if you get saline introduction into that, you're going to kill a lot of plants, and it'll be a lot more expensive to grow your crops on the Delmarva Peninsula. So that could be a way of mapping out where saline inundation is going to happen by matching this impact crater to stuff like that. All right, so 3 of all of the ones that we've had in the past, all the impacts and all of the meteorites and meteoroids that have entered Earth's atmosphere have occurred near the Russian mainland. Why is that? Yeah. It's just really big. Russia is absolutely huge. It is a huge, huge landmass. So the bigger your catchment area is, the greater chance you are of catching stuff, right? So North America as a whole has a bunch too. But it just happens that the political boundaries of Russia happen to be much larger than some of the boundaries in North America. So they catch a lot of these things, and that's why they have so many of them. It's all completely random where they land. So in the past, we talked about this at the beginning of the class, process of uniformitarianism. James Hudson introduced this, and then Charles Lyell really took it further by saying the present is the key to the past. So Earth has to be older than 6,000 years because of all of these very slow, very gradual processes happening over long, long periods of time. Think plate tectonics. How fast are those plates moving? The same rate as your fingernails. That's not fast at all, but it's going on for so much longer that it's able to move continents apart and crash them together. So it's an elegant idea. It's a very far-reaching idea. It's given us the foundation that we've stood upon. And then before that, we believed in catastrophism, where you had an archbishop saying, reading through the Bible, saying, "Oh yeah, Earth started 6,000 years ago on October 21st." And all of the things that are on the surface of the Earth, the mountains, the craters, the seas, were caused by these catastrophic events, huge, huge, devastating events all at once. That's the only way it could have done. So we can actually take a little bit away from this. Because we don't just have these long-term slow events on Earth, even though that's the dominant thing that has defined Earth's history, but we still have these massive impacts from space. All of a sudden, the universe is like, hey, Earth, catch, and it gives us a huge ass asteroid 5 to 10 kilometers wide. That's going to cause a significant geologic impact on the Earth's surface. So if we can refine Hutton and Lyell's idea, we come up with punctuated uniformitarianism, where we have this overreaching, far-reaching, slow geology of plate tectonics, river formation, valley formation, glacial advance, glacial retreats. That's stuff that we've talked about the entire semester. And then we also, at the same time, have all these violent impacts from craters, impact craters, and then what happens afterwards, the immediately rapid extinctions that happen afterwards. So we see these every so often. So that's why it's punctuated uniformitarianism. All that long-term geology is punctuated by significant events that really define certain geologic ages. And that's how we're going to get into mass extinctions. So mass extinctions are, the name says it itself, sudden loss of large numbers of plants and animals relative to new species being added. So we use mass extinctions specifically for boundary conditions. So for the geologic time scale, most of those boundaries are determined by some change happening on the Earth that we can see in the fossil record or the geologic record. So if there's a period of time where there's a big sudden event where tons and tons of things die, we're probably going to put a marker there and say, okay, something happened here, we're in a new time period. So we're going to look at each of these. So mass extinctions usually involve climate change, which is why that when we talk about climate change in today's world, we're concerned because mass extinctions in the past didn't involve humans at all. Now they do. Oh shit, now we got to deal with it. So most of it can happen from plate tectonics. Remember, plate tectonics induces volcanism. Whenever we move continents apart or bring them together, we're impacting where water is going to flow, where those thermohalines, those ocean currents, where they're bringing warm water, cold water, where it ends up. So we can, whenever we bring them together, remember, we're going to have our ice age. When we spread them apart, we have warming periods. So this is on long time scales. So sometimes life on Earth is able to adapt to it, and the ones that can't, they die out, and that may be an indicator of a new age. They cause extreme volcanic events. So we can have flood basalts that we've had in the past, where just these huge igneous provinces where we're erupting so much lava that we're releasing a lot of gases like carbon dioxide, H2O. That's going to contribute to warming. So if we have global warming from greenhouse gas emissions, we can also have it from huge fields of lava if we have enough of it, right? Also, we know that whenever we have these silica-rich explosions, specifically from felsic magma, remember we have all of that high viscosity magma built up on top. Those produce the most ashfall. So whenever we have ashfall, we're increasing the aerosols. Remember those tiny little particulates that are in the atmosphere? And that's going to increase the albedo, the way we can reflect the sun's incoming radiation. So if we can reflect that, we can reflect more of that incoming radiation, we'll have less radiation overall. That means we're decreasing the solar energy budget. We're going to have global cooling. And then we can also have impacts or air bursts. So think of the air burst in 1908 that wiped out a bunch of forest. If it was a little bit bigger and wiped out the entire Siberian forest, we would have an incredible loss of vegetation. We would have a lot of wildfires. So all of that is going to stack up on itself, and we can have cooling. So all that debris is going to block the sun. You're going to have less vegetation. You can increase the acidity of the oceans, all sorts of stuff. So let's look at the big three. So we have the Ordovician extinction event, the Permian extinction event, and the KT boundary extinction event. KT boundary is the big one. So we'll talk about each of these. And we've had a couple of more considered mass extinctions, but they're not as big as these ones. So in this graph here, we have geologic time in millions of years. We have each of our geologic epochs. Nope, periods. Cambrian, yep, periods. And we have the number of genera, or number of genus. So as we can see, with the Cambrian, we have what's known as the Cambrian explosion, where we have just tons and tons of new life coming up. So it's going to continue to grow until we get to the late Ordovician. Right at the boundary of the Ordovician Silurian, we have an event. So remember, the event happened first. We added the boundary there. That's why that boundary is there. That's why we're in the Silurian now, because something happened, caused a lot of death. We're thinking, okay, we're in some new period. We keep going. We have a couple of extinction events, and then we have a big one in the late Devonian. Keep going. We build up again. Life has a way of rebounding, and then we get to the late Permian, and we're gonna drastically decrease, almost back to where we were at the beginning of the Cambrian period, like really, really low amounts of life. Then we're gonna keep going, and then we get to the KT boundary, and we're gonna eventually get back up, but we'll see. All right, so bronze medal, the Ordovician extinction event, the third largest. We had 2 peak dying times separated by 100,000 years. So in terms of geologic time, that's really nothing. So we're just going to count it as one event because it's most likely linked to each other. So remember, at this time we have, we're not forming Pangaea yet. All the continents are still separated. So we have all of these inland seas, these shallow seas. So most of life is aquatic. So this specific event was based on the main dominant forms of life. We have trilobites and we have brachiopods. Trilobites gone, brachiopods gone. Brachiopods, if you're not familiar, they're like clams and mussels, cooler cousin. They have these like interwoven folding shells. They're pretty cool. I have a couple of those fossils at home, I think. So the most likely cause is we transitioned from the warmer period of greenhouse Earth into an icehouse Earth. So all of this ice sheet growth is going to lock up all of that fresh water. We're not flowing into the ocean. The ocean sea level is going to drop because we're locking up all that water in the ice. That's going to give us colder temps. And we're going to, since most of life on Earth at this point is aquatic and it's used to these like tropical lagoonal waters, it's not going to handle really cold waters at all. You can't put shrimp from the Caribbean and drop it into the Bering Sea and expect them to survive. Same kind of thing here. So that's why we have this big dying event 445 million years ago. This is the Permian extinction event, otherwise known as the Great Dying. It was just a real hoot and a holler. So we're killing almost 90% of all life on Earth. So during the Permian, we've got a lot more, still pretty aquatic, but we're starting to develop a little more land-based plants. So we've got a lot more plants on the land, as well as our stromatolites. Those algal masses are going to develop on the coastlines. So the most likely cause of this is the Siberian flood basalts. Remember, there are these huge fissures in the Earth's surface. They're bringing up huge amounts of lava and huge amounts of gas. The key component here is the gas. We have more CO2 coming up from volcanism. We're going to develop more greenhouse gases in the atmosphere. We're going to have global warming events. So one thing to keep in mind with this one is while we have flood basalts in the north in Siberia, at the same time, we're not completely sure yet, but if you go almost 180 degrees to the south in the South Pole, right beneath these ice sheets in Antarctica, there's an impact crater that we've mapped out through geophysics. And based on the age, it's probably happened around the same time as this. So at first people were like, oh, it was an asteroid that hit so hard that it pushed lava through the other side of the Earth. And we're like, no, that's dumb. But an impact crater on one side of the Earth plus a flood basalt on the other side of the Earth is going to be pretty devastating to the entire Earth as a whole. So we're looking into that. Could be another contributor, but the flood basalts here, they're so massive. think of the entire East Coast just covered in lava. That's what kind of volcanic fissures that we're talking about. That's the size that we're dealing with. Huge, huge deposits. Matter of fact, these deposits that happen here form the backbone of most of Russia's mineral economy. Like all of Norilsk, Russia, all that area right in the north is just incredibly, incredibly rich with all those minerals that come up in volcanic events. So, all right, and then we get to the one that you probably know about the most. This is the Cretaceous Paleogene boundary. We had 70% of all genus die off, but we're killing off the dinosaurs, so no more Jurassic Park. But that ended up being good for us because at this time, dinosaurs are obviously the dominant species on the planet. They're huge, they're predators, they got sharp teeth. Mammals live at the same time, but they're super small, they're super cute, they're super cuddly, and apparently delicious to dinosaurs. So with the great dying of the dinosaurs, we have this global cooling event that helps to pave the way for mammals to become more dominant on the surface of the earth, and that makes way for us. So the reason we know so much about it is we have 3 different sources of data. So this is Lewis and Walter Alvarez. They worked in Italy, and they found this specific outcrop. And discoveries in geology are sometimes not very exciting or sexy. Because this literal boundary right here is the thing that changed our entire conception of this specific mass extinction event. Just that line from there to there. Doesn't make for a great photograph, but this is a really, really important outcrop. Because it's such an important outcrop, it's protected by law today. It's the boundary between these 2 great ages. So the first that we have is, if we're looking at these layers, we have in the clay layer in between them, we have super enriched iridium. Now, iridium is a very, very rare earth element. Usually it is only found in spaceborne rocks, in asteroids and meteorites. So because we can find this in this layer, most likely, since it suddenly appeared out of nowhere, probably from a meteorite. The second one, we have fossils. So if we are looking in one outcrop and we see fossils, and we look just a couple of feet above it and we see no fossils, something happened where things were not alive anymore to die and deposit their fossils there. So, and that's not just from one outcrop. Once we have an outcrop, we're able to identify similar age outcrops in other continents and other areas, and we're able to cross-reference those and get a better data set for that. Then the third, which was the last one we were able to find, is we found the Chicxulub crater right off the coast of the Yucatan Peninsula. We didn't have the technology for a very, very long time to scan and look at that area below the surface of the water, but now we do. So let's break this down into a sequence of events of what happened at this specific impact. Excuse me. So we have our asteroid moving at 30 kilometers per second. That is 67,000 miles per hour. That is a pretty fast moving rock. So we're approaching, we're coming in, we're building up our heat from all that friction and our airflow flowing over that rock, entering the atmosphere. Boom, we're gonna hit the Earth right off the coast of the Yucatan. So the immediate impact is going to create 200-kilometer diameter crater that's 40 kilometers deep. So number one, you're creating a void space that large, huge. So the initial shock wave, we're gonna melt rocks, we're gonna crush them, we're gonna vaporize some of them if they're small enough. And then afterwards, all of that rock is going to be thrust out and fall as like a blanket in the surrounding area. Just like you would with a nuclear bomb, an impact crater creates a mushroom cloud just based on its trajectory and the forces that come out of it. So all of that cloud debris, the dust, the rocky material, it's going to rise up. It's going to go all over the stratosphere. It's going to block the sun. We're increasing our aerosols. We're going to increase our albedo, our reflectivity. Going to get less incoming radiation. At the same time, like this is a super hot thing that's coming into impact with the Earth. So it's going to create a fireball and it's going to set off a bunch of wildfires. So it's going to create a wave of dry air followed by a fireball. That's going to spell disaster for any forests in the surrounding area. So all of the rocks at the bottom of the ocean here, they're rich in sulfates. If we're vaporizing those on impact, we're sending all of that sulfuric acid into the air. So if we have all of that into the air and we're going to rain that down as acid rain, that's going to impact pH of our oceans, of our lakes, of our rivers, going to make them really uninhabitable for a lot of aquatic life. Then, of course, just from that impact, we're going to have a tsunami. Huge, huge tsunami, over 300 meters high. And that's going to continue for a couple of days just from the sloshing, because you've created that depression in the middle of the ocean. Now we move to a month later. We still have all of these aerosols up in the air, so we don't have any sunlight. Earth is really dark. So if we don't have any sunlight, we don't have any photosynthesis. If you don't have photosynthesis, you don't have leafy plants for certain dinosaurs to eat. If you don't have dinosaurs that eat leafy plants, you don't have predatory dinosaurs to eat upon them. You have a disruption in the food chain. So all of these are going to die out. You're still going to have that acid rain. And then after a while, you're eventually going to get back to a more stable area. You're going to preferentially rain out all of that acid. So we're going to dilute all of those acids in the water. We're going to get our sunlight coming back as the aerosols settle out, find a place to sink. And then we're going to get our plant life back and eventually go back to normal. But most of life on Earth has already gone several months without sunlight, without food. It did not do well. However, mammals happen to do very well. They were small, so they didn't require a huge amount of food. They were covered in hair, which enabled them to survive in colder temperatures, unlike cold-blooded cold-blooded reptiles like dinosaurs. So mammals end up being the dominant species in the aftermath of this. So lucky us. Go mammals. So we've talked about mitigation strategies and adaptation strategies for every other hazard we've talked about in this class. How do you mitigate or prevent an asteroid hurtling towards the Earth? You don't really. This is from 2016, where some NASA scientists were concerned about Earth's planetary defense, which is an actual department of NASA where they track all of these near-Earth objects and anything that could come and impact the planet. So obviously the key is finding Bruce Willis, telling him to fly up to the asteroid, drill into it, and explode a nuke. If any of you have ever seen Armageddon, you will know that it is just a cinematic masterpiece with absolutely no plot holes or scientific issues whatsoever. But we do actually have plans for this. So it turns out it's actually really easy to redirect an asteroid. Number one, anything that has mass has gravity and generates a gravitational pull. So even if you are by yourself in your spacesuit in space, you are generating some level of gravitational pull. Granted, compared to the Earth, a planet, the moon, it's nothing, but you're still generating something. So the idea is if you have some vehicle in space that can move past an asteroid far enough away, you can change the direction and the trajectory of that overall, you can change the overall trajectory of that asteroid. just by pulling it a couple of meters to one direction, that's going to change your entire trajectory completely. It could miss Earth by miles and miles. So turns out it's very easy to do so. The problem is having stuff up there in order to intercept it. So as you know, a lot of you I know are engineers in this room. It takes a long time to design and build something. It takes even longer to permit and test it. So as you can imagine, if we found a near Earth object hurtling towards Earth and we didn't have anything up there already, we would be really hard pressed to get something up there to intercept it and take it into a different direction. So the idea is this mission, which launched in July, the DART, the Double Asteroid Redirection Test. It's basically designing a platform that would stay in orbit. So you already have your vehicle in orbit, and then once you know the trajectory of whatever incoming object, boom, you go out there, you redirect it, everyone's safe. Bruce Willis gets to come home and see his family. So that's the idea behind this kind of stuff. So planning ahead, as with all geologic hazards, is the best thing that you can do. So that's all I have for this entire course, basically. So thank you guys very much for sticking through it. I know it's a lot of material in a short amount of time, but I think you guys have done really well in this class. If any of you have throughout this class have thought, oh, you know what, geology is pretty cool, it might be a good career path, please reach out to me. You have my email. I'll be more than happy to set you up on the right path if you ever decide you want to enter the world of rocks and other cool shit like that. But tomorrow we'll have an exam review, probably pretty short, but we're going to cover everything from coastal hazards and climate change to soils, mass wasting, and stuff we talked about today. So I'll see you guys tomorrow, and then I'll see you for your exam on Friday. So have a good one, everybody.
Thank you, Professor.
Thanks, guys. Have a good one.